The solar system, in all its beauty and vastness, has always opened itself before humanity with a feeling both familiar and enigmatic. Within its quiet yet unwavering orbits, between the sun's gentle glow and the cold, beckoning darkness farther out, hundreds of moons drift endlessly, like silent companions to the planets. Thinking of them feels like stepping into a vast cosmic library, where each moon is a book holding its own history, geology, climate, and a constellation of unanswered questions. From tiny bodies only a few hundred meters across to immense worlds larger than rocky planets, they all turn together in a quiet symphony shaped by time and gravity. As of March 25, 2025, the confirmation of 891 moons in the solar system is not just a scientific milestone. It's a reminder that the universe is always richer than we imagine. Among them, 421 belong to the major planets, including Pluto, and the rest follow dwarf planets, asteroids, and icy objects scattered far beyond Neptune's orbit. Each moon seems to carry its own origin story. Some were born beside their parent planets. Some were captured from distant and unfamiliar regions of space, and some emerged from violent collisions in the solar system's turbulent youth. Of the 174 moons officially named and recorded orbiting the 6 outer planets, most belong to the 2 great giants, Jupiter and Saturn. They are empires of moons, where dozens of worlds move under the command of immense gravity. Yet what makes moons truly captivating is not just their numbers, it's their astonishing diversity. There are bright, icy surfaces like Enceladus, scorching volcanic worlds like Io, methane seas on Triton, and sponge-like tumbling bodies such as Hyperion. No 2 places are alike, even though they all belong to the same star system. To scientists, these moons are not simply inert rocks circling their planets. They are unfolding stories, active worlds marked by intricate processes. Some hide oceans beneath thick ice sheets, where liquid water may rise and fall with internal heat. Others carry their own magnetic fields, almost like miniature planets. Still others bear the scars of spectacular ancient impacts, their vast craters holding echoes of a chaotic beginning. Thinking about how these moons are distributed throughout the solar system, one can imagine a vast family in which each planet carries children with their own distinct personalities. Moons that orbit close to their parent planet often follow smooth, circular, predictable paths. They were born from the same disk of material, raised in the same environment, and share familiar traits. Farther out, however, the odd and irregular moons move on tilted or stretched, or even backward paths. They are the strange visitors held in place by gravity, travelers from faraway regions who bring with them stories of origins lost to time. Watching the steady rise in the number of known moons over the decades, one realizes how much of the universe remains unexplored. With every new telescope brought online, with every spacecraft venturing just a little farther, more moons appear. And perhaps the most humbling thought is that 891 is nowhere near the end. Astronomers believe thousands of tiny worlds still hide in the darkness, waiting to be seen. They may be just small chunks of rock a few kilometers wide, but each one holds clues that help us understand the solar system's formation and its long, intricate dance. The idea of a moon stretches far beyond physical presence. It leads us to questions about life, planetary evolution, and the conditions that make liquid water possible. When we think of Europa or Enceladus, curiosity stirs about the oceans beneath their ice, kilometers thick and eternally sealed from sunlight. Could anything be living beneath that frozen silence? Are chemical processes quietly unfolding in a place where light has never reached? Thoughts like these make the study of moons feel not only thrilling, but profoundly hopeful. It is striking to realize that these moons, mere satellites of their planets, can offer environments richer than some rocky worlds. Some have atmospheres thicker than Mars. Some contain global oceans. Some hold more water than all of Earth combined. In the stillness of space, wrapped in cold darkness, these worlds exist like hidden jewels. And when we step back to look at all this variety, we begin to see how moons give the solar system its depth and vitality. They are records written over billions of years, evidence of collisions, captures, gravitational tugs, and ancient upheavals. Each moon is a chapter unlike any other, and as we read them, the solar system grows more intimate, more meaningful, and infinitely more profound. In the quiet of space, where light travels slowly and time seems to stretch without end, the moons continue their journeys. They keep circling their parent planets, keeping time with an ancient rhythm set long before humans ever looked up at the sky. And as we watch them from afar, a sense of calm gently rises, that even in a universe so vast, we can still find connection in these small, wondrous worlds. Once we've settled into the slow, drifting rhythm of more than 800 moons circling distant planets, a quiet question naturally rises, almost as if whispered from the empty spaces between their paths. How can we possibly sort, classify, and understand such a vast celestial family? From this grand tableau of countless tiny worlds turning before us, the next step in understanding them is to find a sense of order within their beautiful chaos. And that is where the idea of fundamental classification becomes essential. When scientists look closely at the motion of each moon, they begin to notice two distinct groups, like two major chapters within the larger story of the solar system. Each group carries its own traits, reflecting its history, origin, and the journey that shaped it. Understanding these two groups is more than simply naming them. It's opening the very first doorway toward deeper insight into how moons interact with their parent planets and with the environments around them. The first group consists of what are known as regular moons. Their orbits are round and steady, moving in the same direction as the rotation of the planet they belong to. They travel gently near the planet's equatorial plane, as though they were born from the very same disk of material that once swirled around it. These moons are seen as the planet's true children, formed at the same time, raised in the same environment, sharing similar compositions and structures. Observing them, one can easily sense the stability in their orbits, the fullness in their shapes, and the harmony in the steady rhythm they have kept for billions of years. They are the planet's natural extension, the outcome of a shared creation. The second group, larger and far more varied, is made up of irregular moons. These moons may orbit in the same direction as the planet, but many move in the opposite direction, counter to the planet's own spin. Their paths are often tilted, stretched, distant, sometimes long, loose arcs curling across space. They move in ways that make them feel not entirely native to their surroundings. And indeed, they are not. Most irregular moons are believed not to have formed alongside their planets. They once traveled independently through the solar system as small worlds of their own, until one day, the gravity of a giant planet captured them, like strong arms closing around a wandering guest. The capture might have followed a collision, or simply occurred through a delicate balance of speed, distance, and timing. Comparing the two groups reveals two very different origin stories. The regular moons tell a story of shared formation, shared growth, and shared evolution alongside their planets. The irregular moons tell a story of wandering, of long journeys before finally being caught and claimed by gravity. The two groups exist together, complementing one another like two distinct chapters in the same vast book of solar system history. Their differences go far beyond their orbits. They lie deep in their nature. Regular moons tend to be nearly spherical, shaped over eons by strong gravitational forces. Their surfaces often show the marks of long-term tidal interactions, stable heat, clear structure, and a history of constant shaping. Irregular moons, meanwhile, are often smaller, more oddly shaped, and many have rough, cratered surfaces, as though still carrying the untouched memory of the distant regions they once drifted through. They hold within them a kind of ancient echo from the solar system's chaotic past, an era of collisions, deflections, and gravitational whirlpools. What is most remarkable is that despite their opposing origins and paths, these two groups have coexisted in stability for billions of years. Their shared presence allows scientists to unravel the deeper dynamics of the solar system. By studying the steady orbits of regular moons, researchers can trace back the early formation of planets. By analyzing irregular moons, they can reconstruct how small bodies were exchanged, pulled off course, or swept into orbit around the giant planets. Through them, the solar system emerges not as a static structure, but as a constantly shifting landscape where every small world preserves part of its history. These two groups also raise important questions about the potential for water, atmospheres, and geological activity. Regular moons, located close to their planets, often experience strong tidal forces that can generate heat and maintain subsurface oceans beneath thick layers of ice. Irregular moons, more distant and colder, interact less, yet they offer clues about primordial materials and the conditions that existed before the giant planets even formed. Looking at this classification, we see not just two groups of moons, but two ways the universe creates and reuses matter. Their distinction is a reminder that even the quietest, smallest moons contribute profoundly to our understanding of planetary formation. In their steady motions, whether in harmony with their planet or moving against it, they open subtle but powerful windows into a distant past. And as this chapter on basic classification closes, the story of the moons continues to unfold. Each group, whether regular or irregular, leads us toward its own collection of worlds, toward greater richness, deeper variety, and new tales waiting to be told. From this foundation of understanding, we can step farther into the exploration of individual moons, their unique histories, and the mysteries waiting to be revealed in the next parts of this long cosmic story of the solar system. As the moons of the solar system gradually take shape in our minds, through the familiar ideas of regular and irregular satellites, a quiet thought rises from that foundation, as if lifted gently into place. Even though hundreds of moons move through the darkness of space, our journey toward understanding them always begins with one that feels deeply familiar. Amid the tangled swirl of tilted orbits, among a vast family of distant and surprising worlds, there is one moon that humanity has not only watched from afar, but touched, stood upon, and marked with our own footsteps. Once the categories are laid out, once the story has opened with the diversity and origins of moons across the system, it feels only natural that the next step leads us to Earth's moon, the place where humanity's curiosity about natural satellites truly began. The moon is the fifth largest natural satellite in the solar system, and the largest moon orbiting a rocky planet. To us, looking up at the night sky, it often appears as a simple, softly glowing sphere, but its true story is far older and far grander. According to the giant impact hypothesis, a Mars-sized body named Theia collided with the young Earth about 4.5 billion years ago. The impact not only melted the surface of our infant planet, but also launched vast amounts of material into space. Over time, that material gathered together under the pull of gravity and became the moon we know today. Because of this origin, the moon is not merely a passive companion. It is a missing piece of Earth itself, a fragment cast outward during the chaos of our planet's earliest era. What makes the moon extraordinary is not just its size or its birth, but its essential role in maintaining stability on Earth. The moon stabilizes Earth's axial tilt, preventing extreme climatic swings over long stretches of time. Without it, the planet's tilt could vary wildly, leading to unpredictable climate shifts that might have made Earth far less hospitable to life as we know it. Thanks to the moon, Earth has been able to maintain a steady environment, one where water can remain stable, life can develop, and natural cycles can repeat themselves over billions of years. Tides, an inseparable part of Earth's ecological balance, also arise from the moon's gravitational pull on the oceans. These rhythmic rises and falls not only shape the familiar heartbeat of the shoreline, but also helped form coastal ecosystems, many of which served as nurseries for early life. Over billions of years, the presence of the moon has created a stable stage on which life could experiment, adapt, and flourish. Yet despite its importance, the moon retains its solitary beauty. Its surface stretches out like a cold, dry desert, coated in fine regolith dust and marked by thousands of impact craters preserved through deep time. The moon lacks a thick atmosphere to shield it from meteorites, and it has no vigorous geological activity to reshape its surface. Once a scar forms, it remains, almost forever. Each crater is a piece of history, a frozen moment of cosmic time left untouched by wind or rain as they would be on Earth. And on that silent surface, humanity has left its own imprints. When the first astronauts landed on the moon, they left behind traces of a moment when we stepped off our homeworld for the very first time. Without wind to erase them, those footprints may endure for millions or even billions of years. In a way, the moon serves as a natural archive of human history, where small, delicate marks reflect an immense desire to explore. The moon's size brings its own wonders. Though only a quarter of Earth's diameter, the combination of its size and distance makes it appear large in our sky. Because of this perfect coincidence, total solar eclipses become some of the most breathtaking sights in nature. The moon, small in comparison to the sun, can still perfectly cover it when positioned just right, casting the world into a gentle, sudden twilight, leaving only a thin halo of sunlight around its edges. The moon also keeps one face constantly turned toward Earth, while the other, the so-called far side, remains forever hidden from our view. This happens because the moon is tidally locked to Earth, meaning its rotation matches exactly the time it takes to orbit our planet. Through this delicate balance, the moon maintains a stable gravitational relationship with Earth, one that has endured for eons. Looking back at everything, from its cosmic origin to its role in supporting life, from its stark landscape to the historic moments etched upon it, the moon emerges as a gentle anchor for Earth. It is not just a satellite, it is a partner in the story of life itself. And after exploring how moons across the solar system can be sorted and understood, returning to the moon, our one and only, feels like coming home. A place where even the most complex ideas find deeper meaning in a world so near, yet endlessly distant. After following the story of the moon, its ancient connection to Earth, and its quiet role in keeping our planet steady for billions of years, our attention naturally drifts toward the next nearest world in the solar system. The shift feels gentle, like the continuation of a familiar journey. One moment we are stepping away from the moon's still, gray surface, and the next we are moving toward a sky where small worlds hold surprisingly deep mysteries. This brings us to Mars, home to two tiny silent moons whose stories are no less remarkable. While Earth's moon carries a dramatic origin and a profound influence on life, the two moons of Mars reveal a very different beginning, a different path, and a future unlike any other. Mars has two moons, Phobos and Deimos. They are so small that if placed beside the great moons like Triton or Ganymede, they might easily be mistaken for drifting stones from the asteroid belt. Yet their smallness offers a unique perspective on how planets can acquire companions from distant regions. Phobos, the larger of the two, is still modest in size, an irregular world measuring roughly 27 x 22 x 18 kilometers. In the imagination, it resembles a dark, rugged stone that somehow found its way into orbit, carrying a story that may have begun far beyond Mars itself. Phobos orbits extremely close to Mars, so close that a full orbit takes just over 0.3 Martian days. That means in a single day on Mars, Phobos can rise and set multiple times. One can imagine it as a dark speck racing across the planet's orange-red sky, moving far more quickly than Earth's moon ever does. But its closeness is not a sign of deep companionship. It is the sign of an unstable fate waiting ahead. While Earth's moon stabilizes its parent planet, Phobos is slowly spiraling inward. Every century, it falls about 1.8 meters closer to Mars. It sounds slow, but on cosmic timescales, it is a ticking clock. Calculations suggest that in about 50 million years, Phobos may collide with Mars or be torn apart by tidal forces, forming a thin, dusty ring around the red planet. Its future makes Phobos one of the few moons whose destiny we can predict with surprising clarity. Beside it drifts Deimos, smaller, more distant, and also irregular in shape. Deimos does not share Phobos's dramatic fate. Its orbit is more stable, farther away, and less affected by Mars's pull. In its quiet way, Deimos floats through the Martian sky like a light pebble, peaceful and unhurried. Interestingly, both moons are thought to have originated in the asteroid belt, captured by Mars's gravity during a chaotic chapter early in the solar system. This makes them living witnesses to an era of drifting, colliding, and gravitational snaring, when planets were still gathering the shapes we see today. Looking at Phobos's surface, long grooves and deep depressions appear like scars from ancient impacts. The most striking of these is Stickney Crater, a massive structure that dominates nearly one whole side of the moon. That enormous collision is believed to have created the long grooves etched across its surface, like old wounds that never healed. With no atmosphere and no geological activity, Phobos preserves these marks as pages of history left unaltered by wind or rain. Deimos, by comparison, is smoother, less battered, and its greater distance gives it an appearance of slow, gentle motion. Its surface is coated in fine dust, like a thin layer of ash that has settled over millions of years. If humans were to walk on Deimos one day, the experience might feel like stepping into a world where time flows slowly, and every sharp edge has been softened by endless cycles. Small as they are, both Phobos and Deimos offer scientists valuable insights into Mars's evolution. They suggest that the red planet once passed through unstable eras, drawing in or capturing wandering objects. Their present orbits, different in distance, different in stability, reflect a history shaped by Mars's gravitational influence and by interactions that reached far across the solar system. Looking back from Earth's moon to the two moons of Mars, we feel a gentle but clear shift, from a large world deeply tied to its parent planet to two small, solitary bodies drawn into the story of a dusty red planet. Each step opens a new window, reminding us that despite their varied sizes, origins, and destinies, every moon contributes in its own quiet way to the vast, unfolding picture of the solar system. After leaving behind the small yet turbulent stories of Phobos and Deimos, the space around Mars gradually opens up, like a doorway leading into the quiet transition zone between the planets. From the tight orbits where those two tiny moons circle the red planet, the journey moves deeper into the asteroid belt, where countless fragments drift silently through space, each piece like a memory left over from the solar system's earliest days. It is here, in a region that seems simple and still, that a discovery revealed an entirely new way of understanding satellite systems in the universe. For decades, scientists believed that only large planets had enough gravity to keep a moon. Asteroids, too small, too light, often porous and loosely held together, seemed incapable of doing so. Yet in 1995, when the Galileo spacecraft flew past the asteroid Ida in the belt between Mars and Jupiter, an unexpected image appeared. A tiny object orbiting Ida like a true moon. That little companion was named Dactyl, and its existence became a turning point in humanity's understanding of small worlds in the solar system. Dactyl is only about 1.4 kilometers across, far too small to be considered a moon in the traditional sense, yet large enough and steady enough to maintain an orbit around Ida. Before Galileo's images arrived, no scientist had experimental proof that an asteroid could have a satellite. The discovery of Dactyl was like a reminder that the universe is always more surprising than we imagine. It hinted that many other asteroids might also carry tiny, unseen companions. Ida itself, the world Dactyl orbits, is an unusually elongated asteroid, its structure shaped like a heavily weathered stone. Watching Dactyl move around, Ida reveals something delicate in their interaction. There is no strong gravity, no atmosphere, no powerful forces, only a faint pull between two pieces of rock drifting through space. And yet, within that fragility, Dactyl's orbit holds steady, as though the universe is quietly preserving a relationship formed by ancient events. Among the asteroid moons known today, Dimorphos, the small moon of the asteroid Didymos, is the name most often mentioned in recent years. Dimorphos is only about 160 meters wide, far too small to form any detailed surface features. Yet its very smallness made it the perfect target for NASA's DART mission. For the first time in history, a spacecraft was intentionally directed to collide with an object in order to alter its orbit. When DART struck Dimorphos in 2022, the goal was not only to test planetary defense, but also to observe how a tiny asteroid moon responds to an external force. What is striking and quietly thought-provoking is that even though Dimorphos is tiny and Didymos is not much larger, the two form a surprisingly stable system. They orbit each other in a steady rhythm, repeating each cycle like soft, measured steps in the vastness of space. Watching their motion is like observing a miniature version of a planet-moon system, compressed into two small blocks of stone. Their harmony shows that orbital balance is not reserved for large worlds. It can arise anywhere gravity finds equilibrium. These discoveries lead to a broader realization. If small asteroids can have moons, then the number of moons in the solar system may be far greater than we currently know. Every asteroid in the belt, every distant object in the outer reaches of the system, may carry one or several tiny companions yet to be seen. This means our map of moons is still in its infancy, and every mission, every telescope image, could open a new chapter. Comparing asteroid moons with the satellites of large planets makes the differences obvious. With big moons like Earth's moon, Europa, or Titan, we speak of oceans, atmospheres, and complex geology. But with small moons like Dactyl and Dimorphos, the fascination lies in their origins and the fragile perfection of their orbits. They are not worlds harboring mysteries of life, but relics from a chaotic era when the solar system was forming, fragments that never disappeared, quietly holding their paths for billions of years. The existence of these moons reminds us that the universe does not follow simple rules. Not all moons are large or stable. Not all satellite systems form alongside their hosts. Some moons are born from massive impacts. Some are captured wanderers. Some are so small they seem like stray stones. And some, like Dactyl and Dimorphos, exist quietly, yet play a vital role in deepening our understanding of how celestial bodies evolve. From the two tiny moons of Mars to the modest satellites of asteroids, the journey widens, soft and natural, like the very motions of these bodies themselves. The story of moons is not only about size or beauty, it is also about the places where we least expect them. Even in the quietest corners of the solar system, small worlds continue to orbit, to endure, and to tell their own version of the universe's long and intricate story. After leaving behind the fragile stories of asteroid moons, where Dactyl and Dimorphos circle their tiny parent bodies like specks of dust held in place by delicate balance, the journey widens once again. From the realm of satellites no larger than a few hundred meters, our view is gently guided toward one of the most iconic giants of the solar system. The small worlds of the asteroid belt feel like stepping stones, quiet preludes, and now the path leads us into a completely different domain, vast, majestic, and shaped by overwhelming power. This is Jupiter, the planet often called the king of the solar system. Jupiter is the largest planet in the system, a massive sphere of gas more than 300 times the mass of Earth. Its strong gravity not only binds itself together, but also gathers a vast family of moons. So far, 97 moons have been confirmed to orbit this giant. Each moon is part of that great family, shaped under the influence of a gravitational field so powerful it can affect objects far beyond its immediate reach. Among these nearly 100 moons, 4 stand out above all others: the Galilean moons, Io, Europa, Ganymede, and Callisto. Galileo Galilei discovered them in 1610 when he pointed his small telescope toward the bright planet glowing in the night sky. Seeing those tiny moving points of light orbit Jupiter provided crucial evidence that not everything in the universe revolved around Earth. Ever since, these moons have served as symbols, opening the door to the modern way we understand the cosmos. What makes the Galilean moons so captivating is not simply their large size or their visibility from Earth. The true wonder lies in how astonishingly different they are from one another, even though they lie so close together within the same system. Io is scorching and volcanic. Europa is icy, with a hidden ocean below its frozen crust. Ganymede is the largest moon in the solar system and has its own magnetic field. And Callisto preserves some of the oldest surface features known, nearly untouched since the solar system's earliest days. Looking at these 4 worlds feels like reading 4 entirely different chapters of the same cosmic book. But before diving into each of these worlds, Jupiter itself deserves a moment of quiet admiration. It is not only the largest planet, it is the dynamic center of an entire region of the solar system. Its presence shapes the orbits of nearby objects, including many asteroids in the belt. In some cases, Jupiter serves as Earth's protector, capturing or deflecting potentially dangerous asteroids and comets. Yet beneath this immense influence, what fascinates scientists most are the many worlds held in Jupiter's orbit. The Galilean moons are so large that, had they orbited the Sun independently, humanity might easily have classified them as planets. Ganymede is even larger than Mercury. Io hosts the most intense volcanic activity in the entire solar system, its surface constantly reshaped by violent eruptions. Europa, with its smooth, icy shell and long, rust-colored streaks, likely hides a global ocean beneath its surface, one that may hold twice as much water as Earth. Callisto, orbiting at the outer edge of the group, is a time capsule, keeping ancient craters preserved for billions of years. Even though they lie close together, these four moons reflect four very different outcomes shaped by the same set of forces: Jupiter's tidal influence, their orbital interactions, and the conditions present at their formation. Io and Europa feel strong tidal forces, heating Io's interior and perhaps keeping Europa's ocean in a liquid state. Ganymede is massive enough to form its own magnetic field, a trait no other moon possesses. Callisto, farther out, experiences far weaker forces and therefore retains its ancient, untouched nature. The coexistence of these dramatically different worlds within one system leads to an important realization. Under the influence of a giant planet like Jupiter, moons are not merely satellites, they are complete worlds. Each one has its own terrain, structure, history, and potential future. When scientists observe them, they do not see glowing dots in the sky. They see places where water may exist, where energy may flow, and where microbial life might even survive. And so, from the tiny asteroid moons to Jupiter's monumental Galilean moons, the journey expands once more, following the natural rhythm of the story itself. The small drifting rocks of the asteroid belt help us understand the earliest stages of formation. Jupiter's satellite system lifts that understanding to a new level, revealing fully developed worlds, alive with natural activity, quietly unfolding in the shadow of the solar system's largest planet. After taking in the vast portrait of Jupiter and the overwhelming diversity of its Galilean moons, our attention naturally moves toward the world that lies closest to the giant planet. Among the many moons orbiting Jupiter, there is one world so near that it is constantly stretched, squeezed, and pulled by the overwhelming gravity of its parent planet, and by the subtle tugs of its neighboring moons. It is a place where everything happens in extremes, where internal energy erupts as if no escape has ever been possible. From the grand overview of Jupiter's majestic satellite system, the story now draws us closer into one of the most turbulent worlds in the solar system. Io, a moon that knows no peace, home to the most intense volcanic activity anywhere in the cosmic neighborhood. Io is the innermost of the Galilean moons. Its proximity to Jupiter subjects it to immense gravitational forces. But Jupiter is not the only influence. Europa and Ganymede also pull gently on Io through their orbital rhythms, creating a resonance that keeps Io's path from ever being perfectly circular. This constant distortion stretches and compresses Io in a steady cycle, almost as if the moon were being squeezed rhythmically by invisible hands. The result is enormous internal friction, heat generated deep within, powerful enough to melt much of the material beneath Io's surface. Because of this, Io's exterior is not a simple crust of rock. It is a thin shell resting atop a world that is almost entirely molten below. Each time tidal forces act on it, Io's surface can bulge by up to 100 meters, a number nearly impossible to imagine for any solid body. These dramatic changes keep Io's crust unstable, forever cracking and forever pushed upward from within. This is why Io stands as the most volcanically active body in the entire solar system. And the volcanoes on Io are unlike anything found on Earth. Some eruptions are so powerful that material is hurled hundreds of kilometers into space, far higher than any eruption ever seen on our own planet. Certain plumes rise nearly 190 miles high, tall enough that a small moon could fit entirely within the empty space they carve out. As this molten material falls back down, it paints the surface in broad, colorful patches, covering terrain already transformed by previous eruptions. Io's surface glows with reds, yellows, whites, and blacks, not from plants, light, or frost, but from sulfur and its many compounds. These materials are constantly replenished by eruptions occurring across the moon. Some regions may change appearance in just a few months, making Io one of the very few places in the solar system where the surface is reshaped in real time. Io is nothing like Europa's smooth ice, nor like Ganymede with its magnetic field, nor like Callisto with its ancient, untouched surface. Io is a world of violent pulses, of restless energy, of a surface that never stops shifting under the pressure of its own interior. And yet, this extremity is precisely what makes Io such an essential piece in our understanding of tidal forces and how they sculpt celestial bodies. What is surprising is that despite its explosive nature, Io is one of the driest worlds in the entire solar system. It has an exceptionally high density, the highest of any known moon, but almost no water at all. Compared with Europa, whose hidden ocean may harbor the potential for life, the contrast becomes striking. One world promises the possibility of life in liquid water. The other is a furnace where no water can survive. Their closeness in space but sharp difference in nature is part of what makes the Galilean system so unique. Nowhere else in the solar system do such opposing environments sit side by side within such a small span of distance. Io is not just a story of volcanoes, it is a story of interaction. Io shows, more clearly than almost any other world, how tidal forces can shape an entire internal structure. Without the coordinated pulls from Europa and Ganymede, Io would not heat as it does. Without Jupiter's overwhelming gravity, Io would not be stretched enough to generate the heat that melts its interior. Io is a reminder that a world can be sculpted entirely by influences beyond itself, like an instrument producing sound under the touch of invisible hands. From the grand system of Jupiter down to Io, this transition feels natural, almost as if the entire system is inviting us to peel back its layers one by one. From the strength of the largest planet, to the diversity of its 4 great moons, and now to the most fiery of them all, the story continues to unfold gently but irresistibly. Io becomes the starting point for exploring the remaining Galilean moons, each a world of its own, each with its own story, rich, distinct, and shaped by the extraordinary forces that only our solar system can create. After gazing at Io, a world where every motion is amplified into violent eruptions, where the very surface seems to live in a constant state of tension, the mind naturally reaches for its opposite. Among the Galilean moons, it is striking to realize that right beside this raging landscape lies a far quieter world, one whose calm exterior hides a secret, perhaps even deeper than Io's molten heart. If Io is a symbol of intensity, then the next world brings softness, cool brightness, and quiet promise. From the fiery red glow of Io to the pale, still ice of its neighbor, the journey leads us to Europa, a place where the peaceful surface is only a veil over a vast ocean moving below. Europa is the second of the Galilean moons and one of the most beautiful icy worlds in the solar system. Its surface is completely covered in water ice, so smooth that perhaps no other celestial body possesses such a naturally polished, unbroken appearance. There are almost no large impact craters, a sign that the ice is constantly renewing itself, healing, or simply too young to record many scars from incoming debris. Instead, Europa is etched with long, wandering fractures that trace delicate patterns across its frozen shell. These lines, tinted reddish-brown, curl and sweep across the ice like gentle brushstrokes, giving the moon the appearance of a glass sphere threaded with fine, elegant veins. Beneath this icy surface lies what makes Europa extraordinary, a global ocean of liquid water. The outer shell, about 62 miles, roughly 100 kilometers, thick, is only the top layer of a world dominated by water. Current understanding suggests that Europa's ocean may hold twice as much water as all of Earth's oceans combined. This hidden sea is kept liquid by tidal forces from Jupiter. Like Io, Europa is stretched and compressed as it orbits, but not to the point of melting its interior entirely. Instead, the tidal flexing generates just enough heat to keep the ocean from freezing solid. Because of this, Europa is one of the most promising places in the solar system for the possibility of life. Liquid water, a steady source of internal energy, and natural chemical ingredients form the three basic conditions that could allow microbial life to exist. Such life wouldn't need sunlight, perfect for creatures adapted to deep, eternal darkness, relying only on energy rising from the moon's interior. Similar ecosystems exist on Earth in deep-sea vents, where sunlight never reaches, yet life thrives around warm, mineral-rich fissures. On Europa's surface, the long fractures may be signs of activity below. Some may mark places where warmer water or slushy material from the deep ocean pushes upward before freezing in the open cold. This raises the possibility of geological processes beneath the ice that remain beyond our understanding. Some models suggest that massive blocks of ice may drift atop the ocean below, like planetary-scale icebergs moving slowly, silently over an unseen sea. One of the most compelling pieces of evidence for a subsurface ocean came from the Hubble Space Telescope. At various times, Hubble detected plumes of water vapor erupting from Europa's surface, jets that may soar hundreds of kilometers high before falling back down. These vapor plumes act like cold geysers, carrying pieces of the ocean into space. The implications are enormous. If the plumes occur regularly, future spacecraft might collect samples directly from them without needing to drill through tens of kilometers of ice. The presence of this hidden ocean makes Europa one of the most exciting worlds beyond Earth. No one knows what might exist beneath its frozen shell. It could be a quiet, motionless body of water, or it could be a dynamic environment, complete with circulating currents, mineral-rich vents, and sources of internal energy, a combination capable of supporting simple ecosystems. The idea of life existing in total darkness, thriving on internal heat rather than sunlight, stretches the imagination into forms of biology unlike anything humans have ever known. Europa is fascinating for another reason. Its calm, outward appearance is the perfect contrast to Io. Two moons side by side, one blazing with volcanic fury, the other cold yet hiding warmth beneath. One world promises nothing but fire, the other, the possibility of life in an ocean beyond our sight. This contrast enriches the Galilean system. Each moon tells its own story, but together they create a larger portrait of how the universe can sculpt diverse worlds from the same raw forces. Europa's surface, with its smooth ice and sweeping fractures, resembles a map waiting to be read. Each line may record a shift beneath the ice. Each icy plate may hide the memory of a moving sea. All of it suggests that Europa is not still. It lives and changes under the steady rhythm of tidal forces. Europa is not a dead world. It is alive in its own silent, hidden way. From Io to Europa, the journey feels like moving from a land of fire to a frozen ocean that may cradle the seeds of life. One world speaks in eruptions and violent heat. The other whispers through quiet ice and the movement of water beneath. And it is this shift, from fire to ice, from eruption to silence, that makes the exploration of the Galilean moons feel like traveling through different chapters of a cosmic book, each with its own tone, its own rhythm, and its own secret waiting to be revealed. After leaving behind the cold, mysterious beauty of Europa, where a thick, translucent blanket of ice hides a silent, world-spanning ocean, the journey naturally continues outward through the Galilean system. From that serene world, our view shifts to a place that feels more solid, larger, and richer in structure. Beside Europa lies another moon, one so vast that its size alone could convince anyone it might be a planet if Jupiter were not holding it so firmly in its gravitational embrace. From Europa's fragile ice, the story leads us to Ganymede, a magnificent world where many strange and remarkable features coexist as if it were the most natural thing in the universe. Ganymede is the largest moon in the entire solar system. Its size even surpasses Mercury's, making it a fascinating exception among planetary satellites. Yet despite its immense scale, Ganymede is not a planet. It is part of Jupiter's orbiting family. This simple fact is a quiet reminder of how powerful giant planets can be, capable of capturing worlds that might otherwise stand alone in distant corners of the cosmos. Ganymede's surface is a mixture of ice and rock. Two distinct types of terrain stretch across it. Dark, ancient regions covered with countless impact craters, and brighter, younger zones marked by long grooves that hint at past tectonic activity. Though not as volatile as Io or as youthful as Europa, Ganymede carries the signatures of many ancient disturbances etched into its outer shell. The coexistence of old and new landscapes makes its surface feel like an aged map, where every ridge and patch of ice preserves a fragment of history. One of Ganymede's most extraordinary traits is that it possesses its own magnetic field, the only moon in the solar system known to have one. Though far weaker than Earth's, Ganymede's magnetic field still carves out its own space, interacting with the solar wind and Jupiter's enormous magnetosphere. This remarkable feature reveals that Ganymede contains a molten, metal-rich core beneath its surface, much like the rocky planets. Few ever imagined a moon could be so internally complex, but the presence of this magnetic field has reshaped our understanding of what moons can be. Ganymede does not stop there. Beneath its thick outer shell may lie a multi-layered ocean system. Models suggest that Ganymede's ocean is not a single body of water like Europa's, but instead a stack of several ocean layers separated by rigid sheets of ice. This creates a structure reminiscent of a many-layered cake, where alternating bands of water and ice form under shifting heat and pressure. Ganymede's ocean may be deeper than Europa's, though the thicker ice above it means that the way water interacts with the rocky floor could be very different. An important factor when considering whether life might exist there. Another fascinating aspect is Ganymede's role in the orbital resonance shared with Europa and Io. Together, the three moons follow a rhythm of 4-2-1. Every time Ganymede completes one orbit, Europa completes 2, and Io completes 4. This synchronized dance not only stabilizes their orbits, but also influences the tidal forces each moon experiences. Though Ganymede feels these forces less intensely than its two inner companions, it still participates in this celestial choreography. receiving just enough tidal stress to maintain a subtle degree of internal heating. Seen from afar, Ganymede's blend of bright and dark terrain gives the impression of a world both mysterious and quiet. The dark, cratered regions recall the chaotic youth of the solar system, while the bright, grooved regions show that geological activity once reshaped the surface. Together, these contrasting landscapes turn Ganymede into a natural archive of cosmic history, holding memories across billions of years. Compared to Europa, Ganymede feels like an older, sturdier sibling, less delicate, less smooth, but possessing a profound internal depth. If Europa is a hidden ocean and Io is a turbulent firestorm, then Ganymede is a fusion of stone, ice, history, and magnetism. It is not extreme, yet not serene, not frozen in time, yet not wildly active. It strikes a balance that makes Ganymede one of the most complete and fully realized worlds beyond Earth. From Europa to Ganymede, the journey feels like moving from a shining sea of ice to a vast, structured landscape carved by deep time. Each moon carries its own signature, and when placed beside one another, they form a rich collection of worlds circling Jupiter. Their diversity reinforces a powerful truth. The universe never creates two places exactly alike, even when they emerge from the same environment at the dawn of creation. After immersing ourselves in the vast and majestic world of Ganymede, where its magnetic field, molten core, and layered oceans create a richness rarely found elsewhere, the journey naturally turns toward another member of the Galilean family, one that carries an entirely different mood. If Ganymede feels like a mature world full of history and inner strength, then the next destination feels like an ancient chapter preserved almost untouched through time. From a world shaped by internal forces, the story shifts gently to a place that seems to stand outside the realm of change. Callisto, one of the oldest natural museums in the entire solar system. Callisto is the outermost of the Galilean moons. Its great distance means it experiences far less tidal influence from Jupiter than the others do. Unlike Io, which is constantly stretched and heated, unlike Europa with its hidden ocean beneath the ice, and unlike Ganymede with its internal evolution, Callisto exists as a nearly silent celestial body. And it is this stillness that has allowed Callisto's surface to become a record older than anything else we know. Callisto's surface is considered the most ancient in the entire solar system. Its craters date back more than 4 billion years. For nearly the whole history of the system, its surface has remained virtually unchanged. There has been no tectonic activity to raise new terrain or cover old scars. No lava flows to smooth away craters. No deep oceans to melt the ice and form new landscapes. Callisto is like an ancient tapestry woven during the solar system's earliest days and left intact ever since. Its surface is so heavily cratered that it is difficult to tell where one impact overlaps another. Callisto is the most cratered object in the solar system. No matter where you look, the same familiar shapes appear. Rings and circles layered upon each other like the markings of a chaotic era when young celestial bodies collided, shifted, and fought for space. But Callisto holds more than small impacts. It also contains one of the largest structures ever discovered. Valhalla, the largest multi-ring impact basin in the solar system, spreads across an astonishing 3,800 kilometers. Its concentric rings radiate outward from a central point, resembling waves frozen in time after an unimaginably powerful impact. These rings extend for thousands of kilometers, forming a structure unmatched anywhere else. Looking at Valhalla, one can almost sense the raw force of the collision that shaped it, echoing from a time when the solar system was still finding its form. What makes Callisto remarkable is not just its age, but its isolation. Being so far from Jupiter spares it from the intense radiation that surrounds the giant planet. Jupiter's radiation belts can be devastating for spacecraft, but the region around Callisto is relatively safe. This unique feature makes Callisto one of the leading candidates for future human outposts. The idea of choosing Callisto as a base for deep space exploration comes not only from its lower radiation, but also from its stable terrain. There are no volcanoes, no cracking ice, no tectonic upheavals. Callisto is a literal solid foundation. Its surface, unchanged for billions of years, suggests that any structure built there would remain undisturbed by sudden planetary shifts. But what does Callisto offer beyond ancient history? It gives humanity a window into the solar system's past. Its countless craters speak of a time when every world, large or small, endured relentless collisions. If Europa is a promise of life, Io a symbol of extreme energy, and Ganymede a testament to complexity, then Callisto is a guardian of memory. It is a natural museum where every mark is significant, and every indentation tells a story from the dawn of time. And Callisto may offer more than history. It may offer hints of the future. A human base here could serve as a stepping stone for journeys toward the Kuiper Belt, or the distant moons of Saturn and Uranus. Its location beyond Jupiter's harsh radiation makes it one of the few places near the giant planet where humans might stand in relative safety. Interestingly, despite its ancient stillness, Callisto may also hide a subsurface ocean, one far less active than Europa's or Ganymede's, but still possible. If this is true, then even this quiet world could harbor simple life beneath hundreds of kilometers of ice. No one knows for certain, but that mystery is part of what makes each Galilean moon worth exploring in its own unique way. From Ganymede to Callisto, the journey feels like stepping from a dynamic, evolving world into a vast archive of the solar system's earliest memories. The transition feels like moving from a living library into a grand museum, where every patch of ground preserves the history of the cosmos. And it is this contrast that completes the Galilean quartet. Each world a unique tile in the mosaic of Jupiter and the many mysteries that orbit around it. Leaving Callisto, where every indentation on its surface is a relic of an ancient age, the journey seems to shift into a new chapter, lighter yet broader in scope. After traveling through Jupiter's moons, from the fiery world of Io to Europa's hidden ocean, from Ganymede's powerful structure to the preserved history of Callisto, the gaze naturally moves outward, beyond the space dominated by Jupiter. And then, at a greater distance, another world appears like an expanded page in a cosmic book, a place where beauty becomes its own definition. The journey now arrives at Saturn, the planet adorned with one of the most iconic sights in the universe, its wide, shimmering rings glowing softly in the distant sunlight. If Jupiter is the symbol of power and mass, Saturn is the symbol of elegance. Its rings, though made of small pieces of ice, create an image that feels perfectly balanced, as though the planet were wrapped in a delicate, sparkling ribbon. But beneath that beauty lies a staggering truth. Saturn has 274 moons currently announced. This number far surpasses that of any other planet in the solar system and stands as a testament to the extraordinary gravitational reach of this giant. Among these hundreds of moons, only 7 are large enough to reach hydrostatic equilibrium, meaning their own gravity has shaped them into spheres. The rest, with shapes of every imaginable kind, scatter from close to far, forming a rich and diverse population. No other planet hosts such an expansive family of satellites. Each moon is a small piece of that vast space, contributing to the intricate design that orbits Saturn. Saturn's rings, the feature that makes the planet immediately recognizable in any image, are composed of countless particles of ice. Some grains are no larger than sand, while others reach hundreds of meters in size. They reflect the faint light of the sun, giving the rings the appearance of being lit from within. Up close, the icy particles never sit still. They move, collide gently, and settle again under simple physical laws, creating a system that feels alive despite its fragility. If there is any place that displays the delicate artistry of gravity, it is Saturn's rings. Saturn differs from Jupiter not only in appearance but also in internal energy. It is less massive, yet its history is no less compelling. Many theories suggest that the rings may once have been a moon torn apart by tidal forces, or remnants left over from Saturn's formation. Though their origin remains debated, the rings serve as a reminder that in the universe, the most beautiful things sometimes arise from the most powerful events. Looking at Saturn's many moons, one sees an astonishing diversity. Some moons are simple and tiny, little more than icy lumps in stable orbits. Others have unusual shapes, sculpted by processes we can only guess at. And then there are the larger worlds, with atmospheres, subsurface oceans, and complex geology. Among them, Triton and Enceladus stand out, each carrying a sweeping scientific story of its own. But all of them exist within the same grand picture: Saturn's rich satellite system, where ice, rock, and time combine to create unique worlds. What makes Saturn special is not only the number of moons, but also the structure of their orbits. From the small, fast-moving moons close to the planet, to the distant ones drifting at the edge of Saturn's influence, each moon contributes to the system's shape. Some tiny moons even sculpt the rings themselves, creating gaps or waves inside the delicate bands. The interaction between moons and rings is like a dance that has continued for billions of years. When compared with Callisto, where time seems frozen, Saturn offers a sense of graceful motion. Callisto preserves the past in silence. Saturn embodies the present with its spinning moons and shimmering ring particles. Moving from Callisto's ancient stillness to Saturn's refined elegance feels like stepping from a quiet gallery into a grand, sunlit hall where everything moves, yet everything remains in harmony. Each moon in Saturn's system has its own story. Some formed alongside the planet, some were captured by its gravity, some have been coated in ice over millions of years, and some have undergone dramatic changes that make their structure unlike anything else in the solar system. Big or small, each satellite contributes to a richness almost impossible to describe fully in words. In the grand tapestry of the solar system, Saturn holds a special role, not just the planet of beauty, but also the planet of diversity. Its delicate rings and countless moons make it feel like a miniature cosmos of its own, a place where every motion has meaning and every body participates in a shared, intricate balance. After taking in the grand portrait of Saturn, a planet wrapped in the elegant glow of icy rings and surrounded by a satellite system so rich it feels like a miniature cosmos, our attention naturally moves toward the one name that rises above all the rest. Among the hundreds of moons circling the planet, there is a world cloaked not only in ice and rock, but in an atmosphere so thick that it becomes more mysterious than almost any other place in the solar system. From the shimmering curtain of Saturn's rings, the story glides softly toward a moon where a hazy golden veil obscures the surface from direct view. That world is Triton, one of the most promising destinations for exploration anywhere in the solar system. Triton is the second largest moon in the solar system, surpassed only by Ganymede. But what makes Titan extraordinary is not its size, it is its atmosphere. Titan is the only known moon with a dense, fully developed atmosphere, a grand organic cloak made mostly of nitrogen and methane. This mixture gives Titan its soft, orange glow, as though the entire world is suspended in an eternal sunset. The thick haze makes it difficult for sunlight to reach the surface, creating an environment wrapped in quiet and cold. This very atmosphere hides Titan's solid core completely. Unlike Earth's moon, where every crater can be seen from afar, Titan's surface is concealed beneath deep layers of methane clouds, turning any attempt to observe it directly from space into a blur. Only when the Cassini spacecraft and the Huygens lander drew near did humanity catch its first clear glimpse of Titan's terrain. And what they found transformed Titan into one of the most captivating worlds in the solar system. Titan is the only place beyond Earth known to have lakes, rivers, and seas of liquid on its surface. But these bodies of liquid are not made of water. Titan's rivers and seas are filled with liquid methane and ethane, substances that can remain fluid only in environments of intense cold. This makes Titan feel like an inverted version of Earth, where water exists as hard rock, and hydrocarbons take the role of flowing liquid. Methane rivers carve winding channels into the landscape. Vast, dark seas lie still like deep mirrors reflecting dim light through the haze. Beneath Titan's surface, evidence suggests the presence of a subsurface ocean. This ocean may not be pure water, but a mixture of water and liquid ammonia. Ammonia lowers the freezing point, allowing the mixture to stay liquid even under conditions far colder than any found on Earth. If such an ocean exists, and many models suggest it does, it could span the entire moon, serving as a gentle internal engine of heat. Its presence raises the possibility that Titan is not only home to surface liquids, but also to a layered, dynamic world beneath the ice. Another reason Titan has captivated scientists is its thick, active atmosphere. This environment supports rare processes: soft winds sweeping across dark sand dunes, methane rain falling gently in a cycle reminiscent of Earth's water cycle. Thick methane clouds form and fade. Rivers move across frozen plains. Nowhere else in the solar system, besides Earth, does a world possess a full surface-wide cycle of liquid weather. Titan stands as a unique example of just how varied planetary environments can be. Because of these features, Titan is considered one of the best places in the solar system for flight. Its dense atmosphere provides strong lift, while its low gravity makes powered flight extraordinarily efficient. This rare combination inspired NASA's Dragonfly mission, a rotorcraft planned for launch in 2027. Dragonfly will soar across Titan's diverse landscapes, gathering data from hydrocarbon lakes, organic plains, and even regions that may hold clues to prebiotic chemistry. Every flight Dragonfly makes will unveil part of the story Titan has kept hidden for billions of years. Within the soft, muted glow of its methane atmosphere, Titan holds not only scientific data, but also hints of how life might emerge under conditions completely unlike those on Earth. Titan's frigid surface is rich in complex organic molecules, the building blocks of life in many chemical scenarios. If there is any place in the solar system that can evoke memories of early Earth, but in an entirely different form, it is Titan. The transition from Saturn's broad, luminous elegance to Titan's shadowed mystery feels natural, like stepping from a bright, vaulted hall into a warm, dim chamber filled with dense, quiet air. Saturn offers grace and grandeur. Titan offers depth and enigma. One place is beautiful for its structure, the other for its potential to harbor life and complex chemistry. And among Saturn's many moons, Titan is the stop that makes travelers linger a little longer, listening for the whispered story of a world both familiar and wonderfully strange. After passing through Titan and drifting within its thick golden haze, a world filled with cold, flowing liquids, the journey through Saturn's satellite system seems to draw us closer to places that may hold the potential for life. Titan feels like a distant echo of early Earth, transformed into a strange mirror world where methane plays the role of water. But as Titan closes its chapter with its still hydrocarbon seas and gentle methane rains, our gaze is naturally drawn to another realm, smaller, brighter, and carrying scientific hints even deeper than Titan's. A world whose appearance alone makes it look as though it glows softly in the dark. That world is Enceladus, an icy jewel of Saturn where powerful signals of possible life wait quietly to be understood. Enceladus is one of the brightest objects in the entire solar system. Its surface is blanketed with fine water ice, reflecting nearly all the sunlight that reaches it. Seen from afar, Enceladus appears not just white, but almost glass-like, cold, polished, and radiant, as if the moon were carved from frozen light itself. Its brightness is not only beautiful, it is a sign of an environment coated in pure ice, one capable of preserving tremendous secrets beneath its surface. While Titan hides its terrain under a thick atmosphere, Enceladus reveals its truth through dramatic activity. The Cassini spacecraft, one of the most important missions ever flown around Saturn, discovered towering plumes erupting from Enceladus's south pole. These plumes are not merely vapor. They contain methane, carbon dioxide, ammonia, nitrogen, and countless tiny ice grains, all shooting upward from long fractures called tiger stripes. The ejected material falls back like a delicate icy mist, part of it accumulating on the surface. Some particles even escape Enceladus's gravity entirely, contributing to Saturn's glowing E-ring. These plumes are vivid evidence of powerful internal activity. Their existence means that beneath Enceladus's thick, icy crust lies a large reservoir of liquid water, warmed by internal energy. Cassini's data confirmed that Enceladus holds a global subsurface ocean. This ocean may reach all the way down to the rocky core, allowing chemical interactions essential for life. When Cassini flew through the plumes, it collected complex organic molecules, the very types of compounds considered to be the first building blocks of life. Even more revealing is the subtle wobble in Enceladus's rotation, detected during Cassini's close passes. This gentle sway suggests the icy shell is not locked firmly to the interior, a sign that a deep ocean lies beneath, allowing the outer layer to drift slightly. Enceladus becomes a rare example of a world where liquid water, internal heat, and chemical complexity appear together. The three key ingredients needed for life as we know it. Enceladus is neither as vast as Europa, nor as massive as Ganymede, nor as atmospheric as Titan. But the combination of ice, a deep ocean, and possible hydrothermal reactions at its seafloor makes it one of the most compelling places to search for life beyond Earth. Its plumes act like natural fountains carrying material from the ocean's depths into space, offering samples of that hidden world without drilling through tens of miles of ice. It is an extraordinary gift of nature, as if this moon is trying to send signals about the mysteries stirring inside it. Inside the ice grains lie organics, methane, and nitrogen-bearing molecules, proof that Enceladus is not a silent block of frozen water. Instead, it resembles a slow-breathing organism, releasing warm material through its plumes and interacting with the space around it in gentle pulses. And with each breath, a small piece of its deep ocean is revealed. The existence of a global ocean beneath such pristine ice gives Enceladus such potential that many scientists consider it one of the most exciting places in the solar system for discovering signs of life. Not because it has a thick atmosphere, nor because its surface is wide or warm, but because it holds the perfect trio: strong internal heat, abundant liquid water, and rich chemical diversity. Each of these once sparked life on Earth, and Enceladus has all three. Comparing Titan and Enceladus reveals two very different worlds orbiting the same planet. Titan rests under its orange atmosphere. Enceladus gleams under sharp, reflected light. Titan offers complex organic chemistry. Enceladus offers a vibrant ocean and thermal energy. The two moons feel like major chapters in the science books of the future, each one whispering its own clue about where life might arise. From Titan to Enceladus, the journey continues like a series of unfolding discoveries. This small world is filled with signs of hidden processes at work. And in the quiet cold of its icy exterior, Enceladus seems to guard a story still untold. A story humanity is learning piece by piece through its brilliant, hopeful plumes. After lingering for a long while at Enceladus, where icy plumes rise like messages sent from a hidden ocean, our journey through Saturn's satellite system is not yet complete. Within the wide, sweeping orbit of this ringed giant, beyond Titan's golden haze and Enceladus's crystalline glow, there exist worlds much smaller. These moons hold no deep oceans, no towering fountains of vapor, yet each carries its own kind of uniqueness. Having explored the places rich with the potential for life, the story now shifts to those small but curious worlds, those geometric pieces of nature shaped over billions of years. These are Saturn's unusual moons, where shape itself becomes the feature that makes us pause and look closer. Among Saturn's hundreds of moons, some attract attention not for life or liquid seas, but simply for the way they look. They are born from simple physics, yet the results are wonderfully unexpected. Their presence reminds us that the universe doesn't only craft round and symmetrical worlds, it also embraces imbalance, distortion, and beauty in strangeness. Mimas, Atlas, and Hyperion are among the best-known examples, tiny worlds that cannot be mistaken for anything else. Mimas, perhaps the most famous of the three, owes its reputation not to size or geological activity, but to a coincidence in appearance. On its surface lies Herschel crater, so massive it occupies nearly 1/3 of the moon's diameter. This giant scar gives Mimas an uncanny resemblance to the Death Star from Star Wars. Nature never intended to create anything related to cinema, yet the resemblance is so striking that Mimas became one of the most talked about moons in the solar system. Though only a small, icy world, it leaves a deep impression simply because of how unusual it looks. Atlas, unlike Mimas, has a gentler appearance, but is just as strange. It features a raised equatorial ridge that makes it look like a flying saucer from science fiction. This ridge is made of fine, icy material that has built up over long stretches of time, as particles from Saturn's rings drift downward and accumulate around its equator. A simple, slow process, yet one that sculpted Atlas in an unmistakable way. Seen from afar, Atlas seems to float lightly among the rings, a delicate, wafer-thin shape formed by natural curves and quiet motion. Hyperion is something else entirely. If Mimas is symmetry disrupted by one colossal crater, and Atlas is the product of icy accumulation, then Hyperion is the embodiment of unpredictability. It is not spherical. Instead, it has an irregular, hollowed shape, like an enormous rock carved by erosion and fractures. Its density is so low, nearly half that of water, that Hyperion seems more like a giant sponge than a solid moon. Its deeply pitted surface gives the impression of loose, dusty material barely held together, just enough gravity to stay intact, but never enough to compress into a smooth form. Hyperion's existence shows that in low-gravity environments with loosely packed materials, celestial bodies can take on shapes that defy expectation. Together, these three moons, each only a small piece of Saturn's vast system, offer a rich look at the many ways the universe shapes its worlds. They have no deep oceans like Enceladus, no thick atmospheres like Triton, but they each hold a story written in their shapes. Their existence reminds us that beauty in space is not only found in harmony, it is also found in strangeness. Each moon is an example of how gravity, collisions, material buildup, and time combine to form shapes that no one could predict. Beyond their looks, these small moons also shape the space around them. Mimas, with its special orbital position, helps carve gaps in Saturn's rings. Atlas interacts directly with the A ring, keeping its edges sharp. Hyperion, though small and distant, follows a chaotic orbit, one of the solar system's rare examples of true orbital instability. The transition from Enceladus to these geometric oddities feels gentle, like moving from a chapter about deep scientific potential to one about nature's creativity. If Enceladus awakens curiosity about life, then Mimas, Atlas, and Hyperion awaken curiosity about form. Each moon hints that matter in the universe follows shared laws, but is equally shaped by its own circumstances. Through them, we gain a different perspective on how celestial bodies form and evolve. In the larger tapestry of Saturn's satellites, these small moons feel like footnotes in a long story, but they are the footnotes that make the narrative richer. They may not be the main characters, yet they complete the portrait of the Saturnian system. And their diversity makes the journey ever more captivating, as if every celestial body is waiting to share its own quiet story, told in the silent language of shape and structure. After leaving behind Saturn's strange geometric moons, where Mimas resembles something from a science fiction film, where Atlas drifts like a delicate storybook saucer, and where Hyperion keeps the porous texture of an ancient cosmic sponge, the journey carries us farther outward into the cold and distant reaches of the solar system. Moving beyond Saturn's rich and bustling domain, the path stretches toward the outer dark, where sunlight fades into a thin whisper and the solar wind loses much of its strength. And there, in the quiet expanse, a pale bluish planet appears, Uranus. Orbiting around it are a number of moons far less famous than Triton or Europa, yet no less intriguing. Among them stands one world whose surface is so chaotic and mismatched that anyone who looks upon it is left with the same question. What exactly happened here? That world is Miranda. Miranda is often given a name that carries a vivid suggestion: the Frankenstein moon. Not because it is frightening, but because its surface looks as though it were stitched together from pieces that don't belong to one another. No single style or texture dominates. Instead, smooth plains lie right beside pitted, cratered regions. Level terrains sit next to rugged, broken blocks cut through by deep canyons and towering cliff faces. Each area looks as if it came from a different world entirely, collected and assembled unexpectedly into one small moon. Miranda is not the largest of Uranus's moons, but it is one of the most striking because of its disorder. Its surface contains geological features that would make any planetary scientist pause. Among the most famous is Verona Rupes, the tallest cliff known in the solar system. At roughly 20 kilometers high, it is twice the depth of the Grand Canyon and nearly 3 times the height of Everest measured from base to summit. Imagining such a sheer wall standing on a small moon is astonishing. With Miranda's low gravity, an object falling from the top of Verona Rupes would take minutes, long, quiet minutes, to reach the bottom. But Miranda does not stop at a single monumental cliff. It also hosts canyons so deep that some have been compared to Earth's own, only scaled up many times. Certain chasms may be 12 times deeper than the Grand Canyon. These enormous fractures divide the moon into sprawling blocks, like shards of a crystal broken apart and then pressed back together. The result is a surface that resembles a torn collage, pieces ripped, rearranged, and awkwardly reattached, yet somehow beautiful in its imperfection. Perhaps the most fascinating aspect of Miranda is the mystery surrounding its past. One popular idea suggests that Miranda was once shattered in a violent collision, an event powerful enough to rip it into multiple fragments. Afterward, the debris may not have drifted away, but instead reassembled under the pull of gravity, forming a new world. During that reconstruction, different layers of material could have mixed, shifted, and overlapped, leaving behind the Frankenstein appearance seen today. If this theory is correct, Miranda stands as a living example of a celestial body rebuilt after chaos. But there are other possibilities. Some scientists believe Miranda's deep scars may have been shaped by tidal forces from Uranus, combined with the moon's unstable orbit in the distant past. Regions might have been stretched, heated, and then cooled again, producing patches of smooth, younger terrain and regions pockmarked by ancient craters. This explanation accounts for the curious contrast between freshly resurfaced plains and untouched, heavily cratered zones. Miranda is, in many ways, a world of contrasts. No other moon in the solar system blends old and new, smooth and jagged, stable and chaotic, in quite the same way. Even when compared with geologically active moons like Io or Enceladus, Miranda maintains a distinct identity. It doesn't erupt, it holds no deep ocean, and it carries no thick atmosphere. Instead, it tells the story of a world shaped by disruption and rebirth. The transition from Saturn's odd-shaped moons to Miranda feels gentle, like moving from one art gallery to another, where the theme is still uniqueness, but expressed in a completely different form. Small moons like Mimas and Atlas are symbols of shape. Miranda becomes a symbol of interrupted and reconstructed history. Each is its own reminder of nature's wide imagination in forming worlds. And why truly is Miranda called the Frankenstein moon? Not because it was crudely stitched together, but because its patchwork surface is part of its charm. A small moon that carries a large story about transformation, survival after chaos, and a kind of beauty that refuses to follow rules. In the distant night around Uranus, Miranda drifts quietly along its orbit, holding a landscape that feels as though it were lifted straight from the universe's own imagination. After leaving Miranda, a world whose surface looks as though it were stitched together from fragments of ancient astronomical memory, the journey continues outward, drifting deeper into the cold, quiet regions where sunlight becomes little more than a faint reminder. Miranda carries the chaos of a past shattered and rebuilt, while the realms beyond Uranus open into a different kind of story, quieter, older, and somehow deeper. From that Frankenstein world, the next step leads to a moon belonging to the last of the giant planets, Neptune. And there, we find a world that not only stands apart, but seems to defy the very rules that most moons follow. It does not orbit in the usual direction. It moves backward against the spin of its planet. A rebellious world carrying secrets from a far more distant origin. Triton. Triton is Neptune's largest moon and the seventh largest moon in the entire solar system. Yet what makes Triton extraordinary goes far beyond its impressive size. The differences begin with its orbit. While nearly all moons circle their planets in the same direction that the planets rotate, Triton travels the opposite way. This retrograde motion immediately marks it as an outsider in Neptune's family. Among large moons, nothing else in the solar system behaves like this. A backward orbit tells us something profound. Triton was not born alongside Neptune. Instead, strong evidence suggests that Triton was once a much larger object, possibly a dwarf planet from the Kuiper Belt, the distant icy region beyond Neptune filled with ancient remnants of the early solar system. Long ago, Triton may have been captured by Neptune's gravity. During that capture, its orbit flipped, leaving it forever traveling in reverse. That single reversal became the signature trait that sets Triton apart from every other major moon. In 1989, Voyager 2 became the first spacecraft to truly see Triton up close. The images and data it sent back completely reshaped human understanding of this distant world. Voyager 2 discovered that Triton hosts active geysers of cold material, a process known as cryovolcanism. Unlike hot volcanoes on Earth, these geysers erupt with nitrogen gas, icy particles, and dark organic compounds. Some plumes shoot several kilometers into the thin atmosphere, drifting sideways for hundreds of kilometers in gentle winds before falling back to the surface. The existence of these icy geysers shows that Triton is not a frozen, silent world. Even at its enormous distance from the Sun, where temperatures are cold enough to freeze nitrogen solid, Triton still has geological activity. That means it must hold an internal energy source, whether from radioactive decay or faint tidal heating left over from its unusual orbit. Whatever the cause, Triton is one of the rare distant worlds that still breathes with internal movement. Triton's surface is uniquely beautiful, like a frozen shell carved with delicate patterns shaped by pressure, cold, and shifting ice. Many areas are so smooth that almost no impact craters remain, suggesting the surface has been renewed in geologically recent times. Other regions hold strange textures, ridges, frozen layers, and patchworks of patterned ice that make Triton feel like a canvas where nature has recorded its own quiet artistry through cycles of freezing and release. Its atmosphere, though thin, is active. Composed mostly of nitrogen with a small amount of methane, the atmosphere is not dense like Titan's, but still strong enough to create winds. Winds that carry Triton's icy plumes far across its plains. When Voyager 2 observed those columns of material rising and drifting sideways, it offered unmistakable proof that Triton is a world in motion, not a static block of ice drifting alone in the dark. Triton is also one of the coldest places known, with surface temperatures so low that nitrogen itself forms a frozen crust. That extreme cold helps preserve its pristine appearance. But beneath that stillness lies constant change. Geysers, winds, fractured patterns, and the backward orbit all combine to make Triton one of the most compelling objects beyond Saturn's domain. One of the most remarkable possibilities is that Triton may be slowly spiraling inward toward Neptune. Because its orbit is retrograde, tidal forces work in reverse, pulling Triton gradually closer to the planet. Far in the future, Triton may cross a threshold where tidal forces tear it apart, turning it into a new ring system for Neptune. That unique fate makes Triton one of the few worlds whose past, present, and future all point toward dramatic transformation. The shift from Miranda to Triton feels like moving from a place of chaotic scars to a world of icy stillness filled with subtle motion. Miranda tells the story of a moon shattered and reassembled. Triton tells the story of a moon captured and forever changed by the pull of a distant giant. One world shaped by impact, the other by gravity's relentless embrace. Together, their stories open a window into the many ways moons are born, altered, and reshaped across cosmic time, leaving Triton, a world that moves backward like a wandering stranger at the edge of the solar system. The journey expands once more, drifting into a realm where sunlight fades into little more than a delicate imprint. Beyond Neptune's orbit, space grows quieter, colder, and broader in a way that even the giant planets cannot replicate. This is the domain of the dwarf planets, small, distant worlds long overlooked, then rediscovered as human understanding widened. And there, among these frozen realms, moons also exist. Not many, but enough to contribute their own distinct chapters to the universe's unfolding manuscript. Stepping from Triton to the moons of the dwarf planets feels like crossing a threshold from one mystery to another. Smaller, quieter, yet no less contemplative. Among the dwarf planets, the most familiar name is Pluto. Once regarded as the ninth planet and later reclassified, Pluto remains a symbol of how scientific perspective evolves. Orbiting beside it is a system of moons arranged in a strangely elegant symmetry. The most prominent of them is Charon, a moon so unusual that its relationship to Pluto does not resemble any moon system that came before it. Charon is half the size of Pluto, an incredibly rare proportion. Typically, moons are small satellites circling a much larger planet. But Pluto and Charon orbit around a shared center of mass that lies outside both bodies, a balance point in space rather than a point buried within Pluto itself. This has led many scientists to view them as a binary system, a pair of dwarf planets revolving around one another in a slow, gentle dance across the dim light of the Kuiper Belt. Charon's surface holds geological clues to a past far more active than its quiet present suggests. There are massive fractures, large patches of ice that appear to have torn open and frozen shut again, and signs that a subsurface ocean may once have existed. Even if that ocean has long since frozen, its former presence reveals that Charon once held internal energy, something not every small moon can claim. In the faint twilight of the solar system's edge, Charon stands as evidence that even small worlds contain remarkable complexity. Farther beyond Pluto lies Haumea, a dwarf planet stretched into an elongated shape by its rapid rotation. Haumea has two moons, Hi'iaka and Namaka. These two satellites orbit a body shaped more like a spinning ellipsoid than a sphere. Their entire system is believed to be the aftermath of a colossal collision in the distant past. That ancient impact not only created the two moons, but also reshaped Haumea itself, pulling it into its unusual, elongated form. Hi'iaka, the larger moon, shines with particularly bright, pure ice. Namaka, smaller and orbiting in a more chaotic path, feels like a surviving shard of that primordial event. The story of Haumea and its moons offers a different perspective on moon formation. Not all moons arise from disks of material orbiting a planet. Some are born from violence, where matter is torn apart, then gathers again into new worlds. This kind of formation resembles a rebirth, where destruction becomes the seed of a new structure. From Haumea, the journey continues to Eris, the second largest dwarf planet after Pluto. Eris played a central role in reshaping the definition of a planet, and indirectly in Pluto's reclassification. It is orbited by a single moon named Dysnomia. Dysnomia moves in a simple yet steady path around Eris, a small point of calm in the distant, quiet borderlands of the solar system. Though not large like Charon or structurally rich like Saturn's moons, Dysnomia represents an aesthetic of simplicity. A tiny moon circling a frozen world where silence reigns over nearly everything. The moons of the dwarf planets may be few, but they reveal a different side of space, solitude and delicate equilibrium. They do not have the immense gravitational pull of Jupiter or Saturn to gather dozens of satellites. They do not carry the fiery histories of Io or the shimmering oceans of Enceladus. Instead, the moons of the Kuiper Belt are remnants, small pieces of nearly untouched material from the earliest days of the solar system. They embody stillness, slowness, and the pure beauty of worlds shaped only lightly by time. The transition from Triton to Charon, Haumea, and Dysnomia feels like turning the final pages of a vast book, where the chapters near the edge slow down, deepen, and settle. These distant moons do not display volcanic fury or bold geological drama. Instead, they whisper their stories through stable orbits and through shapes left behind by ancient collisions. In this way, every moon, large or small, icy or vaporous, ocean-bearing or simply a solitary rock, contributes to the quiet symphony of the solar system. And from here, the journey begins to approach its closing chapter, a look toward the future, where new missions will continue unfolding the stories the moons have been gently murmuring all along, drifting away from the quiet moons of the dwarf planets, where Charon moves with Pluto like a perfectly balanced pair, where Hyakka and Namaka reflect the ancient collision that shaped Haumea, and where Dysnomia circles Eris in tranquil silence. The story begins to open in a new direction. After looking toward the most distant worlds, where darkness outweighs light, the journey naturally invites a question: what lies ahead? The moons we've passed each tell the story of their own past. Yet the future of exploring them is being written now through the efforts of humanity. From the farthest edges of the solar system, the narrative eases back toward the inner worlds, where new missions are taking shape, defining the next steps of discovery. If the moons of the dwarf planets echo ancient origins, then the missions now in preparation represent chapters still sealed, waiting to be opened. Space exploration has never been a journey that pauses. Questions about origins, structure, and the possibility of life continue to urge humanity forward. And so, the future of studying the solar system's moons is no longer just about watching from afar. It is about reaching out, testing, and listening to these distant places with the finest instruments we can create. One of the most anticipated missions is Artemis. It is not merely a return to the moon, but the beginning of building a sustainable foundation on its surface. Artemis will bring the first woman and the first person of color to the moon, marking a new chapter in human history. But its ambitions stretch far beyond that moment. The moon is set to become a testing ground, a place where technologies for deep space exploration can be built and refined, especially for future journeys to Mars. Temporary habitats, in-situ resource extraction, and long-duration life support systems may all begin their first real trials on the world closest to us. Beyond the moon and toward the icy worlds farther out, NASA's Europa Clipper mission carries some of humanity's greatest hopes for answering whether Europa could host life. By making multiple close flybys, Europa Clipper will gather information on the moon's surface, its thick ice shell, its magnetic environment, and, most importantly, its plumes. Those jets of water that erupt from cracks in the ice may reveal the chemistry of the ocean below, one of the most promising places for life in the entire solar system. NASA is not alone in its interest in the icy moons. The European Space Agency's JUICE mission has already launched toward Jupiter's system, where it will study Europa, Ganymede, and Callisto, three frozen worlds with buried oceans and mysterious interior structures. Ganymede, the largest moon in the solar system, with its own magnetic field, and Callisto, whose surface has remained nearly unchanged since the solar system's earliest days, are invaluable targets. JUICE aims to determine whether these moons can support habitable environments, and to better understand how such icy worlds interact with Jupiter's immense gravity. And while Europa and Ganymede draw much of the attention, Titan, the largest moon of Saturn, is equally vital. NASA's Dragonfly mission, planned for launch in 2027, will deliver a flying robotic explorer to Titan. With a thick atmosphere and low gravity, Titan is one of the easiest places in the solar system to fly with rotorcraft. Dragonfly will traverse vast regions of Titan, its organic dunes, its methane lakes, and its frozen plains, studying surface chemistry and investigating whether Titan may once have hosted conditions suitable for microbial life. Looking even farther ahead is the Uranus orbiter and probe, a top priority for large-scale exploration in the coming decades. Uranus is an odd and fascinating world, a planet tipped dramatically on its side, wrapped in a cold, layered atmosphere, and surrounded by a system of enigmatic moons. Among them, Miranda, with its fractured patchwork surface, stands out, but Ariel, Umbriel, Titania, and Oberon are each full of mysteries. An orbiter paired with an atmospheric probe could finally reveal details that humanity has glimpsed only briefly through Voyager 2's distant flyby. The shift from the ancient, silent moons of the Kuiper Belt to the concrete plans of future missions feels like a change in rhythm. The most distant worlds tell their stories through billions of years of stillness. The missions of tomorrow speak for humanity's longing, our desire to understand the place we occupy in the cosmos. The future of lunar exploration is not only about searching for life or chasing the unusual. It is also about stretching the boundaries of knowledge, advancing technological limits, and expanding our view of what humanity can become. Every moon, large or small, remains a question yet unanswered. Every mission is an attempt to bring our collective intelligence a little closer to the truth. And when we look back at the journey as a whole, from Earth's moon to the frozen surface of Europa, from Titan's hazy atmosphere to Miranda's fractured skin, from Triton's backward orbit to the distant moons of the dwarf planets, each world has contributed to a vast, intricate picture. A picture whose next chapter is being written even now, as new spacecraft prepare for their departure. As we look toward the missions preparing to rise from their launch pads, those new spacecraft destined to visit the Moon, Europa, Ganymede, Titan, or Miranda, the exploration of the solar system's moons seems to be expanding without end. Each mission feels like a door waiting to be opened, and the moment that door swings even slightly ajar, the stories these icy, rocky, or mist-covered worlds have guarded for billions of years begin to unfold in the language of data, light, and time. From that vantage point, a gentle shift brings the journey back across everything we have visited, as though after sketching new horizons, we turn to see the entire mosaic those small pieces have created together. It all began with the very first steps, when we looked at the immense diversity of moons within the solar system. Numbers that once seemed dry, hundreds of confirmed natural satellites, became an invitation to awe, revealing a richness that space keeps offering without hesitation. Every moon, no matter how small a speck it appears in the sky, holds its own features, its own personality, and its own untold story. From there, the classification of moons revealed two contrasting rhythms, those in stable, regular orbits, and those in unusual, tilted, sometimes even backward paths. This contrast became the entryway to many small but captivating worlds, from Earth's solitary moon to Mars's two tiny satellites, Phobos and Deimos, racing around the red planet on brief and precarious orbits. Then the journey carried us into a different realm entirely, where even the smallest asteroids, mere fragments of rock and dust, turned out to have companions of their own, like Dactyl and Dimorphos. The existence of those miniature satellites reminded us that no scale is too small to contain a story worth telling. From these tiny worlds, we moved toward Jupiter and its vast domain, where the 4 Galilean moons stood like 4 major chapters of an ancient book. Fiery Io, home to the most intense volcanic activity known. Enigmatic Europa, its thin crust of ice concealing a deep ocean. Immense Ganymede, powerful enough to generate its own magnetic field. And Callisto, a primordial museum preserving cratered memories from the dawn of the solar system. Leaving Jupiter for Saturn brought yet another transformation. The crowded system of moons surrounding its ringed silhouette set the stage for Triton, with its thick atmosphere and quiet methane lakes, for bright Enceladus, sending icy plumes into the dark, and for the smaller moons, Mimas, Atlas, and Hyperion, whose strange shapes make the solar system feel like nature's own collection of curiosities. At Uranus, Miranda shared a very different tale, a surface torn apart and pieced back together, towering cliffs and deep chasms that record a violent and mysterious past. And beyond even that, in the coldest, darkest region, Neptune's Triton appeared. A captured world spinning backward, still maintaining faint but astonishing geological activity. Then, at the outermost rim of the solar system, where sunlight thins and space grows so wide it feels almost silent, the moons of the dwarf planets emerged like the final notes of a cosmic symphony. Charon and Pluto revolved together in a delicate duet. Hyakka and Namaka trace the ancient collision that shaped Haumea. Dysnomia drifts quietly beside Eris in the endless expanse. Each moon is a story, and each story is a slice of the universe. As future spacecraft launch and begin their long journeys, each mission will turn another page, extending the chapters already written. And from this moment of pause, this breath taken before new discoveries arrive, the connections between all these worlds grow clearer than ever. Moons are not just objects orbiting their parent planets. They are fragments of a grand narrative about how the solar system formed, shifted, broke apart, and rebuilt itself. They are worlds of hidden oceans, fragile atmospheres, cold volcanoes, fractures stretching hundreds of miles, towering jets of ice, and craters older than any continent on Earth. Together, they weave a single story, a story that, when told slowly in the quiet of night, allows the listener's mind to soften, to drift, to feel at peace. As these worlds glide past in the imagination, the distance between us and the universe seems to shrink, becoming gentle, familiar, almost intimate. And now, with this 18-chapter journey coming to a close, only a soft stillness remains, as if a gentle melody has reached its final note, leaving a deep, lingering resonance in the mind. Every listener, awake or sinking toward sleep, carries something from it, a fresh curiosity, a broader sense of understanding, or simply a calm peace in seeing the cosmos through a tapestry of gentle stories. The solar system continues to turn. The moons continue along their quiet orbits, and the stories continue to write themselves, little by little, in the silence of space. May this long journey bring you comfort, a small spark of joy, and a restful night of sleep. Wishing you peaceful evenings always, and a heart that stays curious about the vast, beautiful sky.